Alright, welcome back everybody. Last section of the course, section 11.11. This is applications of Taylor polynomials. We're not going to go too in-depth with a lot of the application, just because we are hitting the end of the semester here, but suffice it to say there are a lot of different applications for these polynomials. So Taylor polynomials are used in one way for approximating functions. So we can use them to approximate values of a lot of functions, particularly functions that are not pleasant to work with. So the nth degree Taylor polynomial of f at a is given right here. So this is that general form we saw in the last section. Right, where you take the nth derivative at a, divide by the n factorial, and then times x minus a to the n. Right, that's t, that Taylor polynomial. Since f is the sum, got a little typo here, not the Taylor series, the Taylor series. Since f is the sum of its Taylor series, we know that the Taylor polynomials will get closer and closer to f as n goes towards infinity. Right, the Taylor polynomials, as n increases, get closer and closer to the actual function value. We saw that with e to the x earlier. So we can use the Taylor polynomials, right, the nth Taylor polynomial, as an approximation to f. So f of x is approximately equal to the nth Taylor polynomial, okay, the nth degree Taylor polynomial. Now notice what happens when we use the first degree Taylor polynomial. So we get t sub 1 of x equals f of a plus f prime of a times x minus a. That might hopefully look familiar from Calculus 1. This was the formula we had for the linearization of f at a, right? Or the linear approximation of f. So just, I think, really interesting to see a lot of the tie-ins here to these concepts of the infinite series. So we can get this linearization formula not using any of the calculus, but rather using our infinite series. Okay? But when we're using a Taylor polynomial to approximate a function, the question is, how good is that approximation? Right? That's what we really need to know. Not only because we are approximating, not only what is the value, but how good is that value really? There are three possible methods for estimating the size of the error. So step one, if you have a graphing device available, you can use it to graph the remainder and thereby estimate the error. That's not the most precise way of doing it, though. Two, if the series happens to be an alternating series, we can use the alternating series estimation theorem. And then three, in all cases, we can use Taylor's Taylor's inequality, which says that if the absolute value of the n plus 1th derivative is less than or equal to m, so it's bounded above there, then we have that relationship, the remainder absolute value is also bounded above. And then we can use that to determine the value of the error. Okay? So let's look at an example. So approximate the function f of x equals cube root of x by a Taylor polynomial of degree 2 at a equals 8. So we're going to need a few values here before we get started on this. So I just want to separate this off. You can make a table if you want, you don't have to. Just going to put this off to the side here. So this is all part A here. Okay, so I need f of x. Okay, that's the cube root of x, which we're going to write as a fractional exponent, so x to the 1/3. Then we have f prime of x. That's going to be 1/3 x to the negative 2/3. And then we have f double prime of x, which is going to be negative 2/9 times x to the negative 5/3. Okay. Oops. So then when we're looking to evaluate at a equals 8, then we have f of 8, just the cube root of 8, which is 2. F prime of 8, oops, f prime of 8 is going to be 1/12, and f double prime of 8 is going to be 1 over 144. Sorry, negative 1 over 144. All right, so this gives us the values that we need for our Taylor polynomial, and it's only second degree, so that means we're just going up to the second derivative, so this really is all that we need. So, let's zoom back out here. So our second degree Taylor polynomial that's going to be t sub 2 of x. That is f of 8 plus f prime of 8 over 1 factorial times x minus 8 plus f double prime of 8 over 2 factorial times x minus 8 squared. Okay, and of course, if we were using a higher degree Taylor polynomial, we would have more terms here. But this is just going to be 2 plus 1/12 times x minus 8 minus 1 over, 288, because it's times the 2 factorial there. 1 over 288 times x minus 8 squared. So thus, we have the cube root of x is approximately equal to that second degree Taylor polynomial. So 2 plus 1/12 x minus 8 minus 1 over 288 x minus 8 squared. Alright, so that is our approximation of the function for a second degree Taylor polynomial. Of course, as the degree increases, we've seen the approximation gets better, but that's just what we're working with right now. So next up, for part B, it's asking how accurate is this approximation when x is between 7 and 9? Okay, so as we're around 8, right, so we're within a unit of 8 on either side, how accurate is this approximation going to be? Well, to determine kind of what test we need to use, unfortunately this isn't alternating. It does have some positives, some negatives, but they're not going back and forth, right? We went positive, positive, negative, so that's not alternating. So, unfortunately, we can't use the alternating series estimation theorem. But we can always use Taylor's inequality. Okay, so we can always apply Taylor's inequality to this. So this is going to be with n equals 2, right? That was the degree. And a equals 8. That's where we're centered around. Let me just add a brief... well, let me just do this first. One thing at a time here. So this is going to give us the absolute value of the remainder when n is 2. That's less than or equal to m over n plus 1 factorial, so 3 factorial, times the absolute value of x minus 8 cubed. Okay, and this is where absolute value of f triple prime of x is less than or equal to m, right? F, the n plus 1th derivative. Okay, so in this case, that's the third derivative. So now here's my little note. What is the third derivative? So f triple prime of x. If you continue the pattern from up here, just keep working with that power rule, you're going to get 10/27 times x to the negative 8/3. Okay, so we're going to use that here. So, since x is greater than or equal to 7, we know that from the problem, right? It was told it's between 7 and 9. So since x is greater than or equal to 7, we have that x to the 8/3 must be greater than or equal to 7 to the 8/3. Right? That has to be the case. So, if that's true, then f triple prime of x, which is 10/27 times 1 over x to the 8/3, right, because it was a negative power, that must be less than or equal to 10/27 times 1 over 7 to the 8/3. Right, because of that kind of reciprocal relationship, right, where if this one is bigger than this, then 1 over this one is going to be smaller than 1 over this one. Okay, so, and this number, this is just a number here, we can calculate that. That's going to be under 0.0021. Okay, so since we're able to bound that derivative above by 0.0021, take that to be m, right? Because remember, we're trying to bound it above by m in the function. So take m to be 0.0021. Since x is between 7 and 9, that means x minus 8 is between negative 1 and 1. And then that tells us the absolute value of x minus 8 is less than or equal to 1. Then Taylor's inequality gives us the following. So it gives us the absolute value of r sub 2 of x is less than or equal to 0.0021, right, m over 3 factorial over 3 factorial times 1 cubed, right? Because if we're saying that where we have it, that x minus 8 absolute value is less than or equal to 1, then that's what's going in right here. Okay, and this is just 0.0021 over 6, which is less than 0.0004. So that gives us the remainder is less than 0.0004. And the remainder, again, is that error. Okay, so that tells us how accurate we are. So thus, if x is between 7 and 9, and I'll add the equality in just a second, 0 and 9, our approximation is accurate within 0.0004. And again, that's or equal to on both of those. Oops, sorry about that. There we go. Okay, so a lot going on in this problem. Just remember what we've done here. We approximated the function using a second-degree Taylor polynomial, okay, and then we were able to use Taylor's inequality to determine how accurate that was. And we got within 0.0004 units. So I would say that's a pretty good approximation there. Okay. And then the note here at the bottom just mentions Taylor polynomials also have great application to physics and engineering. You see a lot of those if you go into those fields. But we're not going to take the time to explore that here because I'm sure I've already melted your brains over the last few sections with all of these series going on. But if you are curious, you can go take a look in the book. A lot of interesting stuff in there with a lot of interesting mathematicians behind it throughout history. So yeah, good stuff. But that's it. That's the end of our content for Calc 2. So great job, everybody, making it to the end. I know it's not easy by any stretch, especially not to do it remotely like we're doing it. So great job. That being said, we're going to call it a day here, and I'll talk with you all very soon about what's coming up these last couple weeks. Have a good one.